Bem-vindos ao nosso espaço, um mergulho profundo nos assuntos mais interessantes de esportes, ciências e temas gerais do momento. Aqui você vai encontrar conteúdo de qualidade, com análises empolgantes e descobertas fascinantes que vão expandir seus horizontes. Nossa missão é trazer informação relevante de forma dinâmica e descontraída. Queremos que você faça parte dessa jornada incrível de conhecimento e diversão. Se gostar do nosso conteúdo, não esqueça de deixar seu like e se inscrever no canal para não perder nenhuma novidade. Ative o sininho também. Aproveite!
If you love science, don't forget to like and subscribe. When you hear the buzz of a summer cicada, you probably think of long dormant cycles beneath the soil and the echoing calls that fill the summer air. But beneath these familiar insect sounds lies one of the most astonishing engineering marvels in the biological world. On the delicate, transparent surfaces of a cicada's wings, nature has solved one of modern medicine's greatest challenges, killing deadly bacteria instantly, continuously, and completely without chemicals. For centuries, human medicine has relied heavily on chemical agents, antibiotics, alcohol solutions, and synthetic disinfectants to destroy harmful pathogens. But bacteria are master evolutionary adapters. Through rapid genetic mutation, microbes quickly learn to defend against chemical attacks, giving rise to dangerous superbugs that threaten modern healthcare systems worldwide. Yet, cicadas have remained remarkably untouched by bacterial contamination for millions of years. How do their fragile wings stay sterile in microbe-infested environments without an active immune system? The answer was only revealed recently through high-resolution scanning electron microscopy. When scientists zoomed in on the clear membrane of a cicada wing, they discovered it wasn't smooth at all. Instead, the surface is densely packed with millions of microscopic, pillar-like structures called nanoneedles or nanopillars. These nanoneedles are unimaginably small, roughly 200 nanometers in height and spaced mere nanometers apart, thousands of times thinner than a single strand of human hair. They are organized in a remarkably precise, self-assembling hexagonal grid. When a bacterium lands on the surface of a cicada wing, it does not encounter a toxic, poison or biological weapon. Instead, it encounters a lethal physical trap. To understand how this works, imagine dropping a latex balloon filled with water onto a dense bed of sharp, microscopic posts. As the bacterium makes contact with the array of nanoneedles, strong molecular forces known as van der Waals interactions pull the microbe's cell membrane tight against the textured surface. Because the bacterial cell wall is somewhat fluid and elastic, it stretches downward into the narrow gaps between the individual nanoneedles. As the bacterial cell attempts to move or adhere firmly to the wing, the mechanical stress on its outer membrane increases exponentially. The nanoneedles do not necessarily act like violent daggers piercing straight through armor. Rather, they anchor the bacterial membrane taut while capillary forces, surface tension, and molecular attraction stretch the outer envelope far beyond its structural limit. Eventually, the physical strain becomes far too immense for the cell wall to contain. The bacterial membrane tears open, spilling its cellular contents, and the pathogen quickly disintegrates. This entire destruction process is purely mechanical, governed entirely by the fundamental principles of biophysics, geometry, and surface tension. Because no chemical interference occurs, the target bacteria cannot evolve a biological resistance to the effect. A single cell simply cannot mutate its way out of being physically shredded by mechanical forces. What makes this discovery even more incredible is its biological selectivity. While microscopic bacteria with delicate single-cell membranes are rapidly destroyed upon contact, larger human cells behave entirely differently. Human tissue cells are much larger, more flexible, and structurally reinforced. When human cells touch these nanoscale arrays, their total surface area distributes the force across thousands of nanoneedles simultaneously, allowing them to remain completely undamaged. This natural mechanical phenomenon, known as a bactericidal mechanosensitive surface, has launched a revolutionary wave in the fields of biomimicry, nanotechnology, and material science. Engineers and medical researchers are now reproducing these identical nanoneedle patterns onto titanium orthopedic implants, artificial heart valves, surgical tools, and even public touchscreens. By altering the physical texture of materials at the atomic scale, we can build medical devices that permanently destroy pathogens on contact without ever needing chemical antibiotics. From the humble cicada resting quietly on a forest tree, we have discovered a profound blueprint for a post-antibiotic era. It reminds us that nature's most effective solutions are often built not from complex chemical formulas, but from pure physical geometry. For more incredible facts like this, don't forget to subscribe and turn on notifications.